much, then I can just get going. Okay, the recording is on. Great. Okay. You should be able to see my my screen, my slides in full screen, right? Okay, perfect. All right. Hello, everyone. Thank you for coming or watching this talk later. I'm Yes Khalil. I'm assistant professor of industrial engineering at the University of Toronto, where I carry out research broadly in artificial intelligence, and more specifically in the intersection of machine learning and discrete optimization. So today I'm going to talk about some recent work on machine learning for discrete optimization, where we propose a new recipe for doing this using unsupervised learning rather than reinforcement learning or supervised learning. So as a brief retrospective, around 2012, I left AUB after finishing undergrad in computer science for a master's in computer science at Georgia Tech. And I took a course in advanced machine learning. At the time, graphical models were very popular, Bayesian networks. And the professor proposed to me that I work on some kind of network optimization problem, which I had not seen before. And this was my first encounter with this notion of discrete optimization, which at the undergraduate level, we don't really do too much of because we are concerned with easier problems, polynomial time, solvable problems. And I discovered that there are a lot more optimization problems that are NP complete, but are also very interesting in practice. And so I did my master's thesis on this topic, and I was interested in working on it more for a PhD, but then my advisor says, you need to be more ambitious. A lot of people already do just some kind of network optimization. You need to think a little bit outside the box and try to do more. So in looking for a more promising direction, I started reading and learning about something called mixed integer linear programming, which is abbreviated as MILP or MILP. And that's a general framework for modeling discrete optimization problems, particularly when you have linear objective functions and constraints. And this inspired me to think about whether machine learning can help in solving these very hard NP-complete mixed integer linear problems faster. So I wrote the first paper on that, but there was limited interest from the machine learning community. And I thought, okay, how can I get ML people interested in this so that they can also learn what we're doing in this space? So that brought us to this paper from 2016-17, learning combinatorial optimization algorithms over graphs. So what we did is we tried to focus on combinatorial problems defined on graphs, which is already quite a large class of problems. Many people are interested in such problems. And machine learning people know a little bit more about graph optimization than they know about integer optimization, which is traditionally more of an industrial engineering operations research topic. So we wrote that paper, and since then, there has been an explosion of interest in using machine learning for optimization, continuous and discrete. But a particular paradigm which has been successful is the one we proposed in that paper, which is the combination of reinforcement learning with graph neural network, RL with GNN. And this has led to our paper being cited many, many times. Today, though, I'm going to try to argue against this approach, at least against this approach as the single or most general one. And I'm going to try to also provide an attractive alternative to it. By the way, if there are any questions while I'm speaking, please feel free to ask in the chat or interrupt me if you like. So what were we doing then? I'm going to use as an illustrative problem the minimum vertex cover. So in a minimum vertex cover, you're given a graph like the one on the right. Say it's a graph that represents a social network. And you're asked to find the smallest subset of vertices such that each edge in this graph has at least one of its vertices in the subset, i.e., the edge is covered. and you want to cover all the edges with as few vertices as possible. Now, for this problem, it is known that if you greedily add the vertices where the that belong to the edge, which has the largest sum of degrees of those vertices, then you get something called a 2 approximation, meaning if the optimal vertex cover has size C, this algorithm returns a solution with size no more than 2 times C, which in theoretical computer science is a pretty good result, but it's still not guaranteed to be optimal. So what did we say? We said, if we had such a graph optimization problem, G, and we had a distribution D over problem instances, can we use machine learning to derive better greedy heuristics that work not only on the training problems, but also on some unseen problems that are nonetheless similar in structure? This is the typical assumption that you would use when you set up any kind of supervised learning problem. You say, I have data coming from some distribution D. These data have structural similarities, but they're not exactly the same. And so what's going to happen is we're going to try to leverage their similarities and differences to obtain some model which generalizes to new problems. Here, our problems are instances of, say, vertex cover. The graphs, as you can see, they're kind of similar. It's kind of the same social network, but maybe with snapshots taken at different points in time, such that some edges appear in green or some edges disappear. Can we use this data to learn a better heuristic? This is not limited to minimum vertex cover. You can write a version of this learning problem for other graph problems. Maximum cut, where you try to partition the nodes of a graph into 2 sets such that you maximize the number of edges crossing between the 2 sets. Traveling salesperson problem, where you need to find the shortest route amongst a bunch of cities, and so on and so forth. So for all of these, you can try to think of some kind of greedy algorithm, so an algorithm that incrementally builds a solution, for example, adds a node every step from an empty set, or constructs a partial tour and then adds the next city to it, and so on. So you can think of greedy algorithms for all kinds of graph problems. Can we learn better greedy algorithms? We found that the natural candidate to attack this problem is the reinforcement learning perspective. Why? Because there's a very natural mapping between what you do in reinforcement learning and what a greedy algorithm does. In a greedy algorithm, you always have a partial solution. For example, these 2 blue nodes, that's your partial solution. It's a partial solution because you haven't covered all the edges yet, so you still need to keep going. And that's akin to the state in reinforcement learning. So in reinforcement learning, you have a notion of the state of your decision-making process, of your environment, and the partial solution can be seen as a state. In a greedy algorithm, you have some kind of scoring function, which I'm using these green bars to illustrate here. And that scoring function helps you select the next vertex to add to your solution. In reinforcement learning, there's something similar called the Q function, which basically says, if I take an action in a given state, how good is that action for the future? Last, in a greedy algorithm, you select the best node according to your scoring function. And this is similar to the typical greedy policy in reinforcement learning. So a greedy algorithm can be seen as some kind of reinforcement learning policy. Now, what remains is to try to learn that policy. So for example, for vertex cover, this is the mathematical formulation. You want to set some variables xi to either 0 or 1. These are binary, where 1 means the vertex is added to your solution, 0 otherwise. And the constraints are that each edge E with its endpoints ij must be covered, meaning xi plus xj must be at least 1. So the way we're going to set this up as an RL problem is we're going to say every time you add a vertex to your solution, you incur, here we're going to, think about maximizing reward. So we're going to incur a cost or a reward of -1. Okay, so that when we maximize this, we try to do it in as few steps as possible. And then the state S of the RL agent is going to be the current partial solution. There's going to be an action value function which maps a state and an action, a vertex, to some score. And then there's going to be some greedy policy which picks out the best vertex. So this is going to be the kind of the structure of the reinforcement learning. We've learned this kind of method, and I can show you kind of a sneak peek of what happens. What happens is you do learn some novel, interesting greedy heuristics that can outperform some classical heuristics. So here you're seeing visualizations of two algorithms. One on the left is learned with our method. One is a classical heuristic. And you can see that the one on the left is going to solve the vertex cover problem faster. It's going to cover the edges in fewer iterations. And this emerged through reinforcement learning, which was great. So how did we do that? The first thing is, to do reinforcement learning, you need vectors that represent your actions and your states, so that you can plug them into some kind of neural network that learns the skew function. So the skew function is an estimate of the goodness of a vertex V in a given state ST. And the vector is basically the input here. So what can these vectors look like? Well, you can do feature engineering. You can use the degrees of the nodes in your graph, the degrees of the neighbors of the nodes, sum them up. You can use centrality measures from network analysis and so on and so forth. But basically, you can construct this vector to represent a vertex manually. This is one approach. The problem is that you need to design those features for every task that you're interested in. So in vertex cover, some features will be important that may not be important in the traveling salesman problem. You also don't know in advance if those features are going to be good. Are they going to be predictive of what a good action is? Unclear. Last, such task-specific engineered features may not generalize well if the size of the graph changes. So you get more nodes, more edges, etc. Potentially, those values will not really generalize well. So what's the solution here? At the time in 2016, graph neural networks were starting to kind of arise as a very powerful alternative. And one of my co-authors was involved in research on graph neural networks, or GNNs. So we figured we can use GNNs, since these problems are combinatorial problems, on graphs. So we used a scoring function to represent a node with a feature vector. And we do so by parameterizing a graph neural network. So a graph neural network is just a neural network. It has a bunch of parameters here. I put them in this vector theta. And the way it works, I'm going to show you an illustration before, is by assigning some initial random vectors first to all the nodes, and then having these nodes exchange messages between themselves and their neighbors. And these messages are going to be neural network passes. What this does, though, at the high level, is that it averts the needs for feature engineering. It can be, the parameters of the graph neural net can be learned so that the outcome is good. So you don't have to, you just optimize the parameters of the neural net so that you get good features. You don't think, how do I get good features? You learn the good features. And graph neural networks have the nice property of not depending on the graph size. Okay, so you can take the same graph, multiply its size by 2, and run the same message passing graph neural network and still obtain some predictions, unlike typical neural networks. Now, once we had that in place, we could fold these graph neural nets into a reinforcement learning procedure, for which at the time we used Q-learning or deep Q-learning. And you don't need to read the pseudocode on the left. Simply what this does is, during training, we sample an instance of our problem, say vertex cover. Then we need to pick an action at every step. We either explore, meaning we try actions at random, or we pick the best action greedily according to our current learned network. We update our state. In our case, it means update our partial solution because we've added something to it. And then we do the Q-learning update, which basically says, do a gradient descent step to make your graph neural network parameters theta provide a better estimate of the actual observed reward. So this is a typical RL Q-learning type update. And once you do that, you get an overall framework that looks like this. If you have an instance here of vertex cover, you run it through this graph neural net, which is in this box here. Let's say the graph neural net has 2 iterations. What these iterations are doing is they're taking these vectors associated with the nodes, these squares, and then they're having them passed around between neighbors. And then they get modified based on what the neighbors' vectors look like. And the outcome is that eventually we map each node's vector or embedding to a single score, which is the length of this green bar. And then we take whatever the best node is, and we add it to our partial solution. And we repeat this process. So here you're seeing 2 iterations. At the second iteration here, notice the 2 selected nodes in yellow cover all the edges, okay? All edges have one of these or 2 of these nodes in the set. So that's a feasible solution. In this case, it's an optimal solution. We deploy this not just to vertex cover, as I said, maximum cut, TSP, and so on. And here, the bars correspond to different methods. Ours is the leftmost one in blue, pointed to with the arrows. And lower is better because the y-axis value is the approximation ratio to the optimal value of the problem, which we can compute through some integer programming. So here you can see our methods very close to 1, meaning we're generally very close to optimal, and that we can outperform a number of baseline algorithms, some of which are based on machine learning, others based on classical heuristics or algorithms. All right, so this was great, but what is the limitation? In my opinion, one big issue with RL is that it assumes the environment is a black box. But for a deterministic optimization problem, it is not a black box. The instance has a very well-defined mathematical objective function, minimize sum of I, xi, and explicit constraints, right? For every edge in the graph, xi plus xj must be greater than or equal to 1. The RL doesn't actually use these. They are implicit in it, but the objective goes into the reward function, -1, -1, -1, every time you set an xi to 1. And the constraints are enforced by just restricting the kinds of actions that the RL agent takes. But actually, the RL doesn't know the mathematical structure of the problem at all, even at the superficial level. And this leads to very expensive training. You need to observe a lot of problem instances before you start learning a useful policy. And also, it leads to potentially lack of generalization to similar problems that are maybe larger or maybe have slight difference in structure, because the RL hasn't really understood the core, the crux of the optimization. So that's the limitation on the RL side. On the graph neural net side, there are 3 main limitations. One is applicability. Not every discrete problem is naturally formed on a graph. So here I'm showing you on the right an instance of the very familiar Sudoku. And in Sudoku, there isn't a real graph. It's still a discrete problem. You need to assign discrete values to the empty cells, but there is no natural graph on which to formulate this problem to feed it to a GNN. The other issue is the assumptions underlying a GNN. Because the GNN does message passing between nodes and their neighbors, what you're seeing in the illustration here on the left, the principle here is one of homophily. So like attracts like, meaning closer nodes are kind of similar together. But in an optimization problem, if you think of the nodes as being decision variables, there's nothing to say that nodes that are closer in some relevant graph are more tied together than nodes that are apart. Okay, so that's kind of a key assumption that underlies most GNNs, which is not necessarily relevant to every optimization problem. Last is that the training of GNNs is sometimes hard. they suffer from over smoothing, meaning your predictions, think of it as these green bars, end up being very similar for all nodes in the graph, or for most nodes in the graph. And that's because the messages are being passed around and kind of averaged over the graph. And so eventually you converge to very similar outputs. And that's annoying. And it may limit the accuracy of this GNN, whether you use them in RL or other settings. So the goal in the next part of the talk is to correct course, so to speak, along 3 axes. For one, we'd like a higher level of generality. So we're going to go from graph problems to more general constraint satisfaction or optimization problems. We're going to look at a more flexible neural network architecture. And from that, we're going to transition to the transformer. And we're going to seek out a stronger training signal. Rather than relying on black box reward in RL, we're going to try to use the problem itself to design a what we call self-supervised or unsupervised learning objective. So the picture at the bottom illustrates kind of our main design, which has on the left in blue the Sudoku, which is an example of a non-graph discrete problem. In the middle in green, the transformer architecture, and on the right, the kind of loss function that will be considered. So much of what I'll say next is based on this paper with my students and colleague published at the International Conference on Machine Learning last year. And it puts all these ingredients together. So to get there, we'll first define a constraint programming problem. Constraint programming is a very general language for describing constraints. You can see on the top right corner, I have a link to a tutorial on constraint programming, actual implementation tutorial using a software called OR Tools, which is a very powerful modeling and solving tool for constraint programming. And you can define, using the language of constraint programming, almost every problem you can imagine. So here I'm going to look first at the Sudoku as our main toy example. It's a constraint satisfaction problem. There is no objective function. And it's defined by this tuple, xdc. X is just a set of variables. In Sudoku, these are the empty cells, and you'd like to assign values to them. Oh, I just saw the question. Yes, so I'll get to that. So I'll get to the varying graph sizes with the transformer towards the end. It's a good question. So X are going to be the variables. Each variable is going to have a domain. For example, in Sudoku, a variable xi can be either 1, 2, 3, 4, 5, 6, 7, 8, 9. Assume here for simplicity that all variables have the same domain. And the constraints are going to describe the kind of the rules of the Sudoku. So in constraint programming, you have what we call global constraints. These are very powerful functions that can capture kind of in a very short sentence, very complex constraints. One of them is the all different constraint. So all different between a bunch of variables says every variable in this list must take on a different value from its domain than all the others. So for example, the first line says each row has different values. For example, x11, x12, x13, up to x19, they should all have different values. That's the row constraint. The second one says x11, x21, x31, all the way to x91. Each column must have different values. And then the last one is every 3 by 3 square has different values. So think of this as a language for describing the constraints of the problem. It's a very efficient language and extremely useful. And if you have any interest in this, I really recommend checking out OR Tools. A lot you can do there. Okay, so I'm trying to advocate for moving away from RL. Should we just try to predict solutions directly? Right? On the left, I have an instance of the Sudoku. On the right, I have a solution. Should I just try to learn some kind of box, right? Some kind of machine learning model that takes the input instance, try to spit out an answer. I argue that that's too much to ask from an ML model in a single forward pass. If you think about it, ML models make predictions. by picking up on some patterns, etc., in the inputs. But here it's not a problem of pattern matching, really, right? It's a problem of reasoning algorithmically. And it's unlikely that just one pass over any kind of neural network is going to immediately spit out a correct answer, right? That's going to be hard to train. Instead, we're going to try to learn to do local search. So what is local search? If you think of these dots as being different assignments of values to variables, two neighboring dots are two assignments which differ by, say, only one value. For example, here you have these two assignments. They're exactly the same except for the red value. On the left, it's 1. On the right, it's 2. So these are neighbors of one another. But more generally, you can have a larger neighborhood, and you think of that as a local neighborhood. And local search is basically traversing this sequence of dots by making jumps from one dot to one of its neighbors, and then from that to the next neighbor, and so on and so forth, with the hope of reaching, for example, a feasible solution for Sudoku. So it looks something like this. Let's say now I, put the dots on a 2D grid. Local search, when you're at some kind of red dot here, is going to consider neighbors up to some radius, right, or distance, and try to make a jump to one of them. Okay. So it looks something like this. If we deploy this for Sudoku, you start initially here with a very bad solution. Okay, so everything that is in red is incorrect, meaning it violates at least one constraint of the Sudoku. For example, here 2, 1, 1, the one in the middle, which we assign, is obviously not feasible because it violates the row constraint. It also violates the 3x3 square constraint. And as you traverse the space, making these local jumps, you start to hopefully reduce these red values until you arrive at a nice Sudoku solution. So that's local search. What is learning to do local search is, can we learn to make these jumps from most infeasible to slightly more feasible to feasible? Okay, so from red to orange to green. Why do we need to learn this? Because local search, writing local search algorithms, which are out there, is very hard, right? How do you define the neighborhood? How do you make the jump? Which variables do you change? To what values do you change them? The hope is that, just as we learned a greedy policy, that with data, we can come up with a policy, right, that helps us make these jumps as efficiently as possible. Now, if we want to learn to make these jumps, it's natural to think about supervised learning as an option. I argue that supervised learning in the discrete optimization setting is impractical because it's a chicken and egg problem, right? I want to learn to solve Sudoku. If I want to do supervised learning, I need to know how to solve them so I can get labels, which are solutions, and then learn from that, right? That's cumbersome. So supervised learning is not advised, and that's the reason why people try to do reinforcement learning, because reinforcement learning doesn't require labels a priori. However, it has its own problems. Namely, it requires the design of a complex reward function. Okay. For vertex cover, it's very easy. Every time you add a vertex to your partial solution, you incur -1. How would you design a reward function for Sudoku? That's much harder, right? But now the insight is going to be that the problem definition, the constraints themselves, hold the answer to what our learning signal should be. And this is the self-supervised perspective. So to illustrate this, I'm going to take just one 3x3 block, okay, this one, and I'm going to focus on the constraint defined on that block. This is the all different constraint on x1, 4, 1, 5, 1, 6, etc., etc. This should be 2, 4. And let's think about when this constraint is satisfied. The constraint on this 3x3 square is satisfied when all 9 variables take on distinct values. The fewer distinct values there are, so the more repeated values there are, the larger we should penalize such a solution or assignment. So let's call the function that penalizes an assignment P, and let's call this the violation penalty. We want this violation penalty to be higher when the constraint is more violated, basically. For example, for this assignment, the penalty can be something like 9 minus the number of distinct values in the set of variables. So here, for 996.167.559, if you count how many distinct values there are, you'll see there are 1, 5, 6, 7, 9. There are 1, 5, 6, 7, 9. So there are five distinct values here. So which is far from 9, right? So we're gonna pay a penalty of 9 minus 5 equals 4. Versus here, I've replaced the 7 with a 4. So now I have one more. Actually, this is a typo. Sorry, I've replaced the 7 with a 4 and the 5 here with a 2. So now I have 6 distinct value. 1, 2, 4, 5, 6, 9. 6 distinct value. So the penalty is 9 minus 6 equals 3. And you can see the penalty is lower for the board, which is closer to being feasible. And on the right-hand side, you have the most extreme case when the board is satisfied. And in which case, you get 9 minus 9 equals 0. So no penalty. Okay? So this is a way, using our own predictions, to obtain some kind of signal about how good we're doing. And you can generalize this to other kinds of constraints. So I mentioned the all different constraints, which is in the second row here. Here we have 3 other constraints, cardinality constraints. So sum of xi to xn equals to k. That's one constraint. And then the not equals constraints. 2 variables need to be unequal. For each of these, you can design some kind of penalty function, which is continuous and differentiable, so that we can compute gradients. And we care about that because eventually we want to train a neural network by gradient descent. So we designed some of these penalties for constraint classes that are very common in discrete optimization. These are just a few of them. And here note that the variables xi are something like xi with a superscript j. These are binary or Boolean variables, and they're set to 1 if the variable xi takes on value j, 0 otherwise. And from that, you can design these functions. And you can see these functions, they involve some kind of linear terms in the x's, maybe an absolute value, rectified linear unit, which is a common neural network operator, product of 2 variables, which is also fine, and so on. So now we have a way to, if we've made a prediction, assess how good it was. Remember, we decided not to do solution prediction, but rather to do local search. So how are we going to do this local search? Okay. Here's the setup. In our training set, we're going to create some initial solutions where we're going to fill the board, maybe at random. So you see this one has lots of mistakes. Then we're going to pass this input into some kind of black box, some kind of neural net, and try to make some improvement on it. Move from red, very violated, to orange, slightly less violated. Once a prediction is made, we're going to pass it through a loss function L, which is going to take the input, right, and the model, and it's going to look at the prediction made by this current model, sum up the penalties across constraints, and output a value saying, oh, okay, your penalty is 38 for this board. The nice thing about this single step prediction is that you can repeat it by using the output of a previous prediction. So here I'm going to take the orange board and I'm going to feed it in as input now, okay? And I'm going to try to improve that. And in this illustration, the improvement happens to be a feasible solution, so it incurs a loss of 0, okay? So we're going to try to do local search by learning to make a single step improvement. That single step, by the way, can modify and indeed will modify multiple variables at the same time. You don't need to modify only one, but it will still not modify the full solution in one go. But what is this black box? Right. Let's open it up. To open it up, we need to briefly do a detour onto transformers. And I use some slides from very nice courses at Stanford that you can also look at that are linked here. Transformers are basically a machine learning architecture that takes a set of inputs, think of them as vectors, okay, and maps them to another corresponding set of vectors or a single value. These vectors in the input, we call them tokens, okay? So think of them as a single word in a sentence in natural language processing. For discrete optimization, think of them as the assignment of value to a single variable. So that's a token. And then we're going to try to transform them using the internal operations of the transformer, which are neural network operations, nonlinear operations, to predict either the next word or some classification over the input. And this is indeed how the GPT model works. Next token prediction, it takes all the words that have appeared so far and tries to predict the next one. The key element of transformers is something called attention. This is why transformers do what they do. This is why they have such strong capabilities. On the right here, you have a typical lookup table where I have a bunch of keys. Each key has a value, right? This is like a dictionary in Python. The user gives a query. We check against the keys. If it matches, we return the corresponding value. Okay, so here D matches with this one. The value of that key is V4. We return V4. Attention does something similar. That is, think of it as a softened version, okay? Relaxed version, not a hard, discrete version. We still have keys and values, but now instead of just checking whether the query queue matches a key exactly, we try to do some kind of similarity calculation that says how similar is Q to K1, how similar is Q to K2, and so on and so forth. The strength of the boldness of the lines here tell you how strong the match is. And then we take the values, we multiply them by the agreement between the key and the query, and we aggregate them in a weighted sum. And that gives us the output, which you should think of as some kind of soft query. So here you see you don't get exactly V4, you get a slightly less dark version of V4. And mathematically, this is a very simple operation. You learn a bunch of linear transformation matrices that map an input embedding or an embedding of a token, xi, to a query vector, to a key vector, and to a value vector. And then to check a key against a query, you take the dot product of the two, which is a measure of similarity. And then you normalize these similarities by using a softmax. And that gives you, for every query, how much it agrees with each of the possible keys. Okay, and then you take a weighted sum, and that's going to be your output. So that's attention. Attention is this orange box here. It's the first operator in a transformer. So we use this transformer architecture. And the smart thing about transformers is you can repeat the computation for capital L transformer layers, meaning you can do the self-attention, process the output through some feed-forward networks. You get a bunch of vectors. You run them again through the attention. And now this looping is allowing you to do a little bit of the complicated reasoning required to solve discrete problems. The other ingredients of our recipe are that basically what we do is to tokenize our input. inputs here, remember, are values from some domains. We learn embeddings for each value possible. So for example, the value 2 gets an embedding vector. This vector is learned. The other thing we do is we combine the embedding of the values with what's called a positional embedding. So here, I know that this 2 occurs at cell 1, this 6 occurs at cell 3, 6, or 3, 5, and so on. So what we're going to do is we're going to also incorporate that information into the input to the transformer. And last, we're going to have a mask. This is this ES, which basically says which variables should the network try to modify. So in its output, which ones of these inputs should it try to modify, and it will not modify the other ones. So this is how we represent the input. So again, input to the transformer is this sequence of tokens, 1 per decision variables, 1 per X, okay? And it includes both the value of the assignment and any kind of positional information. The last ingredient here is taking into account the constraints. So some of the variables here have stronger interactions with one another or more direct interactions. So for example, this cell and this cell are in the same row and also in the same 3x3 box. So we should maybe care more about their relationship in the attention than we care about the relationship between this cell and this cell. So we incorporate that information as also as part of the input in this attention. Once we have those vectors, they go into this L layers of a transformer, which then ends up spitting out bars, right, for each variable, a distribution of which values from 1 to 9 should it take on. So here, for example, it says 5, here it says 3, here it says 8. And of course, these are probabilities. And then the probabilities are used to sample the value, the assignment, which gives us some kind of assignment, right? That goes into the self-supervised loss by looking at the constraints and measuring how violated the constraints are. So we call this overall architecture the transformer. Now, to answer the question from Haidar, how do we deal with varying graph sizes in this case? The nice thing about the transformer is that, in principle, it can take on an arbitrary number of inputs. So it's not bound by a specific number. So the operations internally don't rely on there being a fixed number of inputs. So it's very similar to a graph neural network in that way. So it can handle arbitrary inputs as long as you adjust your positional encoding to scale with your input size, then there's no problem with that. And indeed, we do apply our model to instances of varying sizes, as I'll show in the experimental results. So again, we call this overall neural network architecture the transformer or constraint transformer. Since we wrote that paper, we've made 2 big improvements. One of them is we select the subset of variables to modify strategically. So in a first version, these masks, ES, which variables are we gonna try to adjust, were being selected randomly. We would say, let's try to modify K variables at a time and pick the K randomly. Since then, we've worked on making that selection more strategically. For example, some variables may be more important to correct. For example, variables that appear in many violated constraints or contribute most to the gradient of the loss function. So we bias the choice of variables accordingly. That's one. The other one is that we've connected the learning process, the self-supervised learning process, to a new generative modeling technique called diffusion, which is very popular these days, even for language modeling. And it frames this process of local search as kind of an iterative sampling problem. So it has a probabilistic interpretation. And what we've done there is use something called blocked Gibbs sampling, which basically works very well for discrete optimization. And what it says is every iteration, you log a bunch of variables that you want to modify, that you want to not modify, and you try to modify as many the others as much as possible. And as you proceed in later steps or iterations of the algorithm, you anneal the number of things that you are modifying. So you start to modify less. So at the beginning, your Sudoku solution is terrible. Try to modify a lot of it. And then as you converge, now you have to be more sensitive in your changes. And this is very similar to how we as humans solve Sudoku, right? We start by not knowing too much, make a lot of, a lot of choices. And then as we start to fill the grid, we start to be more careful and more strategic. So as a result of this, we can show pretty good results for our methods. The recent version of this, which is not in the paper, which is under review, we call it blocked it. And here I'm showing experimental results on the left on Sudoku, on the right on the graph coloring problem. So the graph coloring problem illustrated at the bottom, you have a graph, you have a bunch of colors, say 5 colors, and you need to color every node such that none of its neighbors have the same color. So this is one instance of that problem for a very big graph with lots of edges. And we compare our method, blocked it here, a couple instantiations of it, against 2 kinds of methods. The ones in the middle are machine learning methods based on either diffusions or transformers or so on, including an earlier version of our work, and OR tools, which is the constraint programming solver I mentioned before. And you can see here that in both of these cases, whether the problems are in distribution, meaning they are similar to what we've seen in training, or out of distribution, OOD, so graphs that are very dissimilar to what we've seen in training. Our method here, at least its most evolved version, blocked it plus AS, which is adaptive search, which basically picks the variables to modify intelligently, achieves very good results. So on Sudoku, it can solve 100 or 93% of the instances, finding a solution for all of them. And on graph coloring, it also achieves pretty high rates, 83% here, even on graphs that has not seen in training and that are much larger, 54%, and so on and so forth. And these rates, interestingly, are competitive with what OR tools does, which is a very powerful exact solver. So in conclusion, my advice, if you're interested in learning for discrete optimization, is to exploit explicit known problem structure. Don't leave it to RL to discover that through the black box reward. But RL can still be useful for dynamic optimization problems that are naturally sequential, where the full problem formulation is not really provided in advance, and you need to kind of discover your options as you go. But last but not least, transformers are extremely useful, not just for GPT and natural language processing. They are very general architectures that can take sets of inputs and transform them very non-linearly. And so I recommend trying them if you have a problem similar to this. Okay, with that, I thank you for your attention. This is my email if there are questions later when you're watching the talk. And if there are any questions now, I'm happy to take them. Okay, Haidar, I hope I answered your question. Okay, failing instances, which instances did it make mistakes on? Okay, that's a very good question. So I can use these tables to give you a sense of what's going on. So where is there a room for improvement, particularly as problems get larger? The learning becomes much harder. So for example, here for graph coloring, even though we train on instances with 100 vertices and 10 colors, when we test on instances from that same distribution, we get only a 53 or 54%, which is still competitive with some other approaches, but very far, obviously, from 100%. So where could these methods be going wrong? Well, the method is iterative. And it's very likely that it needs many more iterations to converge to a solution. And also there's the fact that the learning itself is bound to be imperfect. And last, because we're using this kind of transformer, the learning, what you learn is still a bit of a black box. So you don't always know if you're learning the right strategy or a strategy that just happens to work well in training. And so for future work, we're interested in trying to learning models that have a little bit more structure in the policies that they learn. How does this compare against classic GNN plus RL? I would say, graph coloring is one example of that. Probably much better. I would say the RL methods here are not being used as much anymore since people realized we can use the problem information much more efficiently. The other problem is scalability. So RL, for example, for graph coloring, here we have number of training instances probably in the thousands. I don't remember exactly how many training instances. RL would probably require a lot more, maybe 10 times more. So that's an issue. So in some cases, it's even hard to get the RL to run at all. The other problem with RL is you can't even scale it sometimes because, or you can't even define it well because the reward function is not trivial, right? So for example, for graph coloring, what are you going to do? Are you going to count the number of conflicts, or just designing this reward function for the sequential process is not easy. So we don't compare to it directly here. Okay, great. So if there are no other questions, I'll thank everybody for attending or watching online later. And if you have questions for me, please feel free to send an email. Thank you, Hassan. Thank you, Haidar. And Haidar, if you can send me a link to the recording, if it's available anywhere that I can share with students or something, please let me know. Okay. Amazing. All right. Thank you both.